stores or loads the firmware. The firmware is stored in an DDR flash, in a DDR SDRAM chip. Where is it? Can I see it right now? I think here. Yeah, and we also talked about bootkits and manipulated firmware, what we can do about it. Basically, not that much currently. Yeah, and now, so yeah, to summarize everything we talked about last time, the assumption or the simple assumption that the hardware tells the truth if you access it directly isn't necessarily correct. The firmware can currently only, so there is this risk of bootkits, and the firmware can currently only be verified with the manufacturer's help. Yeah, and the simple remedy would be signed firmware updates, but as far as I know, we still don't have that. So that's all on HDDs. Today we want to talk about SSD technologies. And I assume that there are no questions so far regarding the stuff we talked about last time. Is that correct? If not, type something in the chat. Okay, let's start with SSDs then. So what are SSDs? SSD stands for solid state drive. It's a data storage based on semiconductor components or flash chips. Here you can see the inside of an SSD. You can see several NAND flash chips, raw NAND flash chips. Yeah. And the term drive actually, like, it remains from hard disk drive, so it's actually not a drive. There are no mechanical parts, but the SSD emulates a hard disk interface, and there are no mechanical parts in it. It's more robust and quieter and also more shock resistant. So I don't know if we talked about that, you probably already know, but if one of your HDDs falls on the floor, it's probably broken. I mean, we also talked about the fact that digital evidence or traces are very hard to destroy. You could probably still read some of the data, but you would have problems if your HDD falls on the ground. If your SSD falls on the ground, it's also not super good, but not as bad as with HDs. Okay, so here you can see like a graph representing the insides of an SSD. As I already said, you have several flash chips on your PCB. You have some kind of power supply. You have a controller. And this controller handles like the communication to the outside and also the emulation of a hard disk. You have this host interface thing here, and not always, but sometimes you also have DRAM chip here. And the flash chips, the flash devices can be read in parallel to increase data rates. So your SSD is usually also much faster than your HDD. And yeah, this is because you don't have any mechanical parts, and you also are able to simultaneously read your memory banks. So this is called a memory bank. Okay. So in SSDs, you have two very important terms or units. There is the page, the page is the smallest unit that can be written. It's usually 2 to 16 kilobits big. And you have a block, and the block is the smallest unit that can be deleted, and it's usually 4 to 8 megabytes. And yeah, this is kilobytes, this is megabytes. So multiple memory cells are grouped into these erase blocks. So these blocks, and these blocks, in addition, are divided into pages. And yeah, as I already said, this is a minimum unit for erasing data, which means that if a single page shall be overwritten, the entire block must be erased. So therefore, the valid data of other pages must first be copied to another location and then written back again after overwriting. And the reason for this differentiation is yeah, the erasing process requires the application of a high voltage in several steps and the shielding of neighboring areas of cells from unwanted interferences, and the checking, so the reading of all cells, yeah, to determine whether the erasing process was successful must be yeah, performed. So you have to shield other cells, and you must be sure that the checking or reading was successful first. And there are 4 strategies how to deal with this write and read processes, or write and erase, not read, write and erase processes on SSDs. So here you can see one strategy. We have a block X here with 8 pages, and we have 4 pages where data is stored and 4 pages which are currently empty. This is the starting situation. This is the legend, you can ignore that. So these 4 are free, these 4 store data currently. So what we want to do is we want to delete, let me check that. So we want to overwrite a page. Yeah, we want to overwrite a page. So in order to do so, we have to save the entire block X to the DRAM buffer. Then we delete block X. Yeah, we delete block X. We write the saved block X back to the deleted block X. So we delete block X, we change something, we write block X back. But while we do that, we also change the content of the page we want to change, or we update it while writing the block back. This is strategy 1. And strategy 2 is we save the entire block again in the DRAM buffer. We mark the block, all pages in the block, as invalid. Then we write the data we want to change in another block, block Y. And then we'll update our page. So block X is now marked as invalid. We write to a free block, to a free page on a free block, and then we'll update page V. Was that understandable? Okay, there's a question in the chat. You can only write on deleted pages, so simply overwriting is not possible. Or would update from 0 to 1 be possible and just 1 to 0 not possible? Um, no. Okay. So the thing again is that you want to write a page. So the smallest unit that can be written is a page. I think I confused myself. The smallest unit that can be deleted is a block. So you could write a single page.
क्या करना है अभी? 1 घंटा है मेरे पास। क्या करना है उसके बाद? उधर मैं चली
Give me a
जाऊंगी।
second.
कब आएगी? 2-3 घंटे बाद। हम्म, हम्म। तो तू उठी इसलिए थी कि उठ के फिर से सो जाओगी। हाँ कह सकते हैं।
Okay, let's walk through strategy 1 again.
तो बस मैं तो आगे करूंगी बैठ के और
We have a block X.
पता नहीं
We
होगा
want
क्या।
to update page 3.
वो पीठ दिखाते हैं जब ऐसा आता है। मेरे को
And in order to do so, we have
फिर
to
टूट गया। हाँ ना।
copy the entire block
मुझे अच्छा लगता
to the buffer,
है। एक तो
delete the
दांत कैसे
block,
बनना।
and while we write the buffer data back to the block, we update page 3. That's the writing process. I think that is a little bit confusing here. So this is there are several strategies
सब दे दे
to write
और मैं लिख के
pages
दे
and delete blocks. So don't take that too serious while we talk about the strategies. So strategy 1 is
दूंगा। मैं
copy
कहता था
block to the
वो इसको
buffer,
बोला था कि
write the
मैं
buffer
नीचे चला
back
गया
to the block,
मेरे
and
को पता
while
है
do
नीचे बैठा
so,
है हाँ मैं इसको
update the
बोला था।
page you want to update. Okay?
मैंने बोला था
And
मेरा
the
ऐसे है
second strategy is
लेना है कि
basically
नहीं
the
बोला।
same, but you don't
गलत
delete block X, you mark it as invalid. And you don't write to the block X again, you write to block Y. So you take a new block and overwrite the new block with your buffer data and the updated page. Okay? Sorry for the
नीचे
confusion.
रुकी इतनी बेशरम आ रहा था तू तो ये कुछ शर्म है तो क्या
Okay,
है
and as I said, we have 4 strategies. So here
छोड़ दे मुझे
come another 2. So strategy 3
तेरे
um,
तो चीज देता
works as follows. We have block X again. We have data in 4 pages. We have data in, we have no data in these 4 pages.
ऐसे
And
तू
we
मुड़ेगी
want to
तब मैं
write a
सोचेगा
page again.
नहीं बात करूंगी मैं तुमसे क्या
And
क्या
in order to do so in strategy 3, we
अच्छा
mark
यहाँ
this
बोलूँ मैं
page we want to update as invalid.
एक मिनट तुम्हें तो एक
Um,
तू तुझे प्लीज मैं आगे
take
रख देता तेरे
a free page in
यार
the
तू
same
यहाँ पे आ मैं तो
block,
आगे नहीं इधर होगा
write
तेरे
the
से शायद
updated
ज्यादा ही
data in this page,
तू सुन मैं केक
and
काट दूंगा
change the LBA address from here to there.
ठीक है
So because it's a logical address, it does not need to
अपडेट ही है ये
have a relation to the physical
तू
location
चला
on the
तू
drive. So
तुम्हारे
we
वाला
we
ठीक है
just pretend that page
जैसे
3
फट
with
रही
the
है
updated data is page 5 is
थोड़ा सा
with the
उसने हटा
updated
दिया
data is
रिफ्लेक्ट
page 3.
फट
So we
रही
just
नहीं ये चुप रहो पूरा
yeah
फटा हुआ माल दिया तो क्या तू
bind
अपनी दुकान से लेकर आई है हमारे घर
bend
पे रुकी है
the LBA address
ये
to
कैसे
another
बंद होगी
page. So this is version 3.
भाई क्या है
It actually shows
काटे हुए
that you
कपड़े
can write
पता
single
नहीं क्या है
pages,
ये क्या है
but with
मुझे
the
समझ नहीं
strategies
आता ये क्या है
before,
इसको क्या
this is
बोलेगा
not
इसको
done.
क्या बोलेगी तू मेरे
but with this strategy, it's done. So you only write one page in the same block. And then there's version 4 or strategy 4, where you do the same thing as with strategy 3, but you don't write to a free page in the same block, but you can also write to a free page in another block. So this page is marked as invalid. You write to another free page in another block and change the LBA address. Okay. Is that clear, or shall I start again from the beginning? So from the beginning means pages and blocks. What happens with the invalidated blocks? Will it be available to write again at one point in the future? It probably depends on the manufacturer of the SSD. So blocks marked as invalid are usually not written again, except you delete the whole block. Yeah, so it actually, the answer is it depends on the SSD manufacturer. Okay, could you explain it again? Okay, let's do it again. Okay. So with SSDs, we have two units, pages, which are the smallest unit that can be written, and blocks, which are the smallest units that can be deleted. Blocks consist of several pages. Here you can see one block with 8 pages. If we would want to delete a page here, we would have to delete the whole block. So we cannot delete the content of one single block, but we can write it. And for writing, there are 4 strategies. The first strategy is we take the whole block, so we want to update one single page, page 3. We want to write it. And in order to do so, we take the whole block, store it in a buffer, and the buffer is, that's why we need the DRAM here. So we take the whole block, store it in the buffer, and then we take the whole buffer, the content of the buffer, and write it back to the same block. But while we are doing that, we update page 3. That's the first strategy. The second strategy is we take the whole block. We still want to update page 3 here. We take the whole block, mark it, we copy it to the buffer. We mark the block as invalid, and then we write the buffer data to another block, block Y. It has nothing to do with this block. It's a new block. We write the buffer data to this block, and while we do that, we update page 3. So this is strategy 2, to write page 3. But as we saw 2 slides ago, pages can also be written. We can also just write one page. This is possible. We cannot erase one page, but we can write one page. So strategy 3 is we have a block. We still want to update page 3. These 4 pages are filled with data. They store data. These 4 pages are empty. We want to update page 3. And in order to do so, we write the updated content in another page, in a free page of the same block. And the original page is marked as invalid. So the block remains as is, but the contents of page 3, the updated contents are in page 5 now. Page 3 is invalid. So we didn't copy the whole block. We just wrote the content in a free page of the same block. Strategy 4 works same as strategy 3. Have a block X. We have page 3. We want to update it. We update page 3 and write the content to another free page, but this time in another block. So in block Y and instead of block X. And we mark page 3, the original page is invalid. So it works exactly like strategy 3, but we don't write in a page of the same block, we write in a page of another block. Okay? Okay. Okay, and invalid pages can only, okay, yeah, so invalid pages can only be used again when the block is deleted. And in order to delete the block, or in order to erase data, the whole block must be deleted. Yeah, active pages in the block hinder deletion. So if there are active blocks, active pages in a block, the block cannot be deleted or the data cannot be erased. And pages are regularly combined into new blocks by the garbage collection mechanism, so that old blocks can be deleted and freed. So invalid pages and data that is marked as deleted can be erased after the garbage collection mechanism reorganized the blocks. And this can be something that is done on demand or in the background. And the mechanism ensures that there's always a certain amount of free pages available that can be written. And there's also such a thing as wear leveling. So the garbage collector is usually connected with something called wear leveling, and wear leveling means that the erase operations are distributed across the entire flash to limit the number of yeah, so we have a limited number of possible program and erase cycles for SSDs, and because you don't want the cell you don't want to damage the cell. Okay, have to start again. So we have flash storage, we have flash cells. We will talk about it today in more detail. And because of the physical process behind erasing data in a flash cell, you cannot do it like unlimited times. After a certain number of program and erase cycles, the cell is damaged. And in order to prevent that, the SSD tries to distribute these processes over the whole SSD, over all NAND flash chips, over all cells, to increase the lifetime of the SSD. So this is wear leveling, and this is also done in connection with the garbage collection mechanism. Okay. And both of these things, so garbage collection and wear leveling, are controller tasks. They are implemented or they work through proprietary algorithms. They also probably depend on the manufacturer. And Yeah, so invalid pages, as page 3 here, are also interesting for forensics because they usually contain old data.
आएगा ऑफिस में वो पता नहीं
Yeah,
दे देगा
but there's another mechanism to get rid of all data, and it's called trim.
आज आके भी
So
कॉफी नहीं बनी
actually accessing invalid pages that would be interesting for forensics because they contain old data is in practice not feasible or not possible because we have garbage collection, we have wear leveling, and we have trim. And trim is another mechanism to get rid of data that isn't needed anymore in order
एक बार
to
हुई और उसमें सारा स्टैटिस्टिक्स
yeah
बता
in
सब
order
कुछ बता
to
दिया और बता
to
दिया कि कितना इम्प्रूव हुआ है
make
वो तो
SSD
प्रॉफिट हो गया
reading and writing,
ठीक है वो
programming
ठीक है
and
और
everything as
ये
efficient as possible.
और भी
So
मैं
the controller
मुझे नहीं समझ आया
tasks
आज
of
तो
an
मैंने कर
SSD
दी
are
आपने
actually
बोला ये
everything the
समझ नहीं आया
controller for HDDs does.
यार
So
डिवाइस इसमें
providing the
वापस
interface
समझ आया
commands,
एक सब समझ आया
providing
मुझे कैसे
everything
समझ
that is
आया
needed to communicate with the
क्या मुझे समझ नहीं
device
आया
the SSD is
मैं
connected
एसएसडी
to.
लगाता हूँ कोई नहीं
But
नॉर्मल
also
लाइक
garbage
नॉर्मल
collection, wear
हाँ
leveling,
है ना ठीक है वो
trim,
आधे लोगों को
over
समझ नहीं आता
provisioning. So over provisioning
मतलब वो
is
मतलब इनको आपस के एक्सेंट नहीं समझ आते
yeah,
मेरे
in
को तो
for
घंटा समझ
over
गया बस आधे मुझे
provisioning is
लगता है कि
something that
नॉर्मल वर्जन है
manufacturers do in order
बाकी को समझ
to
नहीं आ रहा ठीक है
repair
तो कैसे
bad blocks.
तो
So
मैं
the
नॉर्मल
storage on your
वाला एक्सेस
SSD
समझता
is usually yeah higher or greater. You have more storage available than you can actually access as the user because there is this over provisioning area which is used to overcome bad blocks in case a cell is worn out
इससे मेरा
and
कोई
is damaged and cannot be used anymore.
बोलो तो
Then the over provisioning management system jumps in
ये
and
सही तरीके थे ना
tries
एक साल
to
छुपा के
pretend that
दबा के
everything is
बहुत बढ़िया
fine. And the SSD also pretends to be an HDD.
इसको क्या
So
कहाँ पे लिखा
from the
है
outside,
है ना तेरा कोई
from a device
है ना कोई ये क्या है
perspective, it cannot be.
थोड़ा सा
सीधा ले
It's hard to tell if the device is connected to an SSD or HDD,
वो ठीक
basically.
है अंदर ले अभी भी छोड़ देंगे बेवकूफ
Okay, and I know we didn't talk about it yet. We will talk about Slack space in greater detail again in another lecture, but because we are talking about SSDs and HDDs, it is also important to know that there is such a thing as Slack space and that it behaves differently for SSDs and HDDs.
यार ये
So,
सही है ऐसे
what
नहीं
does
बोलते
Slack space mean?
उधर उधर देख ऐसे
So when you write data or file,
नाचता है बहुत सही
the file system
हाँ कर ले
usually clusters sectors or blocks. Sectors or blocks are yeah, the smallest unit
बेसिकली आज
that the
ऐसे
file system can
वही लगा
yeah, not write, but
मुझे काम करने
the
जाना
file system
भाई
reserves
काम कैसे
space
वो
for
एक दिन में
data
बात
or
करते
for
जा रहे थे गियर
files.
मेंटेनेंस करेंगे
And
इसको काम कहते हो तुम काम कहते हो हैं काम कहते हो सर यहाँ पे भी सीधा ये चुप क्यों होगी बोल गई क्या नेट है तेरा या चला गया कोई तो मैसेज डाल रहा था रुको एक सेकंड ये अच्छा मेरा फोन का 30x जूम हाँ ठीक है क्या मेरे साथ में स्पॉइल मिलेगा स्पॉइल मिलेगा इतना क्या हंसी हंसी भी नहीं थी एक एक छोटा सा भी नहीं हंसी थी कुछ नहीं झूठ है तो है झूठ है हंसी तो कुछ भी नहीं थी
Okay. We had some technical issues again. Sorry for that. Okay, let me share the slides again. Okay. So where did the Wi-Fi failure started? We will still at clusters. The beginning of Slack. Okay. Sorry. Okay. Okay. So Slack Space again. Slack Space is interesting because it's basically part of. It's basically reserved space for storing a file which isn't used, and it behaves differently for HDDs and SSDs. It's in Slack Space you can sometimes, depending on the storage technology and the file system, you can find leftover data in there. And this is because file systems usually organize their storage into sectors or blocks. Sectors are usually 512 bytes big, and they are clustered into clusters, like a usual cluster size would be 4 sectors or blocks. And this is, if you want to store or create a file, a cluster is reserved for your file, or several clusters, depends on the size of your file. And if your file is not big enough to fill a whole cluster, then there is Slack Space. So this cluster contains or includes, is composed of 4 sectors or blocks, but the file only needs 2.5 blocks. And so 1.5 blocks are still empty. This is the Slack Space, and there are several kinds of Slack Space. We have the so-called RAM Slack, which is this leftover part of the last sector of the file. We have Drive Slack, which is the leftover part of the cluster. And Drive Slack plus RAM Slack is File Slack. And in this part, in the Slack Space part, you can sometimes find old data which belongs to a file that was written before this file was created. As I said, it depends on the technology and file system, but in the best case, you can find something interesting here from a forensics perspective. Okay, so why am I telling you this? I tell you this because Slack Space behaves differently for SSDs and HDDs. So for HDDs, the Slack Space behaves like I just told you, so you can read it out and maybe find something interesting in the RAM, drive, or file Slack. But with SSDs, it's different because SSDs can only write to pages in previously deleted blocks. The pages that form a possible drive slack after a file has been written are always empty. And with HDDs, there are maybe remnants of a previously written and deleted file at this point.
तुझे तो वीवो लेने
Yeah,
का था।
but not for SSDs. And
जाएगा उसको
मैं
कुछ
कह
yeah,
रहा तुझे तो वीवो
so
लेना था ना अभी तक तो
I
आया नहीं
told you
तेरा वीवो
before that HDDs and SSDs, if you just look at
पापा
the
का
at the
S26 आ गया
storage,
तो S24 लेंगे
at the data itself, they cannot be differentiated, but you could, in theory, have a look at the slack space and try to conclude if it's an SSD or an HDD from the slack space. But we did some experiments on that, and it's not very reliable. Okay, there is a question in the chat. Wait, RAM slack is included in drive slack.
वो जब
For the
स्टार्टिंग में
addition
आया
to
था
make
सब
sense in my head, they should not overlap.
हालांकि वो बात अलग है कि मेरे को जियो सिम चलाना था
उसका नेट पैक फ्री आ जाता ना कुछ ऐसा होता था
1 साल के लिए फ्री था
I think the RAM slack plus drive slack is called file slack, but I can check that again after the lecture.
फ्री में दे दिया and now after this that
Or is,
happened जब उसने पूरी
you're
RAM अपनी
probably
cancel कर दी
right.
then he was making around
Yeah, the drive
350
slack
crores
should end here.
a day
I think that's
in profits
an error on the
मुझे
slides.
यहाँ तो
Yeah, you're right.
मतलब ये वो 350 करोड़ दिन का कमा
Yeah, okay, I think you're right. So this would be the drive slack, and that's the RAM slack, and together they form this is the file slack. If you
तो गलत हो गया
leave that
ये तो गलत
bracket like it is, then it would be the file slack.
थोड़ी मतलब अमीर जगह है अमीर तो नहीं है तो मुंबई में नहीं है
Okay.
हमारे में मुंबई
मुंबई बहुत बड़ा है
Yeah, okay. We talked about trim before. Trim is an ATA command or ATA command, which is a communication standard
$1 billion is
with which the operating system can communicate with the SSD, and it was introduced in 2009, especially for SSDs. And so the operating system actually stores a list of deleted sectors, which it can communicate to the SSD, and the SSD can then mark the sectors as invalid or garbage to include them in the garbage collection process. So the trim is a mechanism for the operating system to communicate to the SSD that there is some data that can be erased. We don't need it anymore. So get rid of it. It must be supported by the operating system. And the operating system actually has no influence on the timing of the garbage collection. So the operating system can tell the SSD to get rid of data, but it cannot tell the SSD when to do it. So in theory, once written to, pages remain in use forever, even if files on the page, even if stuff on the page is deleted, because the SSD does not by itself know that there's no more data there that that is of use. But the knowledge of that is helpful for the ware leveling process, and this is why trim was invented. Okay. Okay, and So Bell and Bodding, they said something about garbage collection and trim. So they said the SSD technology, which is replacing magnetic hard drives inside many computers, is neither simple, well understood, nor homogeneous. Rather, it is complex, poorly documented, and highly heterogeneous. Worst of all, it is active. That is to say, the SSD may act under its own initiative and may undertake quite remarkable and high evidence destructive actions, even if the absence of write commands from a computer, potentially regardless of efforts by the police and forensic analysts to prevent invalidation of evidence. So from a forensics perspective, SSDs are, yeah, quite hard to analyze. Yeah, especially because manufacturers don't publish everything they do with their SSDs. They don't publish how their mechanisms work. They don't publish how their algorithms work, what the controller does, and you actually need to be an electronic engineer or yeah, somebody who really deeply understands the low-level processes of an SSD to actually analyze them. And yeah, digital forensic scientists usually are computer scientists or maybe practitioners, lawyers. Yeah, so SSDs are a real problem for digital forensics,
टोटल 8 ट्यूशन गया जिसमें से मैं
especially because of
छोड़ाता था
all the things we just discussed, wear leveling, garbage collection, trim, but also the read-write mechanisms themselves, the controller,
वो ना
etc.
ऐसी इतनी डिस्क्रिमिनेशन करती थी ना कि एक लड़का आता
So
था उसके
many
साथ गया
many
पोस्टर
digital
किसी का
forensic
नाम था
scientists
मैंने कहा
tried
मुझे किसी का
to
पोस्टर किसी का फालतू काम
investigate,
नहीं करना
especially when
मेरे क्या करूँ
SSDs
सीधा
became
उसके
like
बाद उसको सब
affordable.
बताते थे कि पोस्टर मुझे
Many
देना
digital
मुझे ये
forensic
बहुत
scientists
अच्छा था
tried
मैं इतनी
to
मेहनत करता था फिर
understand their
मेरे पोस्टर का ऐसे
behavior
काट देते थे
from a
ठीक है
digital forensics
तो
perspective.
एक दिन ना क्या हुआ
And for example, to figure out
उसने मुझे ना
what
सुनाया
happens
क्लास के साथ
if
और सारे के साथ
garbage collection, okay, you
मैंने
cannot
कहा
get rid
जो
of
भी
garbage
वीडियो
collection,
वायरल
but
है
you can
वो
um,
उठाया मैंने कहा मैं चला
shut
गया
down trim, for example. And in this
पकड़ के गया
experiment,
बाद में पकड़
for
के
example, Nisbet et al. Tried to figure out how
फंसा क्या मैंने बोला
much
मम्मी को बताना
time it takes for trim
अब
to
निकालती नहीं थी
actually
मुझे कहती सॉरी बोल
communicate
मैंने कहा
to
मैं नहीं
the
बोलूंगा
SSDs
ऐसा
which
मैंने बोला
data
नहीं बोलना
blocks are
पड़ेगा
not used anymore,
फिर ठीक है 2 दिन बाद
and
उसने
for
मुझे
the
लाया
SSD to
फिर
actually
मेरी
get
माँ ने
rid
मेरे
of
को बोला फिर
them.
वापस उसको कर इधर नहीं
So they made some
फिर
experiments
मेरे को अच्छा लगता था
on
लेकिन मैं
that
साइंस
to
की टीचर
figure
नहीं
out
थी
how
मैं ट्राई
long
करता था
it
लास्ट में उसके
takes
बाद
for the
इतने
data
हैरान होती थी
to
जब
be
मैं जिस दिन गया
erased because it's
1 घंटे की
important for
क्लास में आधा
digital
घंटा तुम मुझे
forensics.
ला रही हो मैंने क्लास छोड़
And
दी थी वहां पे फिर मेरी माँ ने एक और ट्यूशन
yeah,
दी
so what they did is
मैनुअल छोड़ दी ना क्लास से
they
फिर वहां
had
पे
a
लिखा हुआ
couple
था
of
कि टॉप करो तो साइंस
SSDs
का लेके आना
with
मेरे को एक
different
ब्लॉक
file systems on it, so NTFS,
पढ़ाया
X4,
मैंने वो छोड़ा
HFS plus.
तो मैंने किसी से
Um,
प्राइवेट ट्यूशन
they
लिया
had
उसके घर
small
जाके
ones, larger
वो समझ नहीं
ones.
आता था मैं क्या पढ़ाऊँ
They had trim enabled, they had no trim enabled, they had high usage, low usage, low activity, like several different parameters. And what they did is every single time they wrote data and immediately deleted afterwards. And then they checked how long it takes the SSD to get rid of the data.
वो आने लग गए
And what they found out was that trim generally shows a very aggressive behavior and that the data was already gone after a very short time.
गाने से पहले मैं
Um,
सुबह 6:30 उठा
yeah, so
मैं इतना कन्विंस किया हूं ना खुद को
this
कि
is
सुबह
after
मैं उठ
1 hour,
जाऊंगा
this is after
और
5 hours.
मेरे साथ भी करता
Yeah,
था
you
मेरे
can
साथ
check
भी
out the
करता था
table
अब मैं थका हुआ था
later,
फिर
but what you
मैं
actually
मम्मी को
see
बोला
from
क्या
the data is
मैं फिर
that
सोया
that
7:30
trim is very aggressive and the
फिर
data
सो गया
doesn't linger on the SSD for a long time. But this was in 2013, so yeah, it's actually time to repeat the experiment and see if trim still behaves like that. But back then it behaved like that. What it tells us is that for SSDs we cannot assume to find old deleted data.
क्या करूंगा मैं उस बाल की PhD करके मैंने
तूने नहीं मत कर
Okay, we already talked about over provisioning.
मेरा
So SSDs usually contain, or the 10% of the SSD storage is usually reserved for over provisioning. It's there to repair bad sectors, to improve the write performance on disks that are highly utilized, and therefore have only a few options for garbage collection. Over provision is actually comparable to the HBA and DCO. So people could try to have a look at the over provisioning area.
मैं तो कॉपी बोल रहा हूँ मेरे को डायरेक्ट
Yeah,
तेरे
to find hidden data is probably
भी करता है
it's probably not that easy to hide data in the over provisioning area of an SSD, but people could have a look at it. Yeah.
ये पूरा एरिया इतना खाली है ना अंदर
Okay, so that was it on SSDs. We'll now shortly have a look at storage interfaces. Are there any questions on SSDs? Okay. Okay, so storage interfaces. There are a lot of storage interfaces out there, so we will only talk about the most important ones. I already told you that ATA or ATA is a standard communication protocol. So many of these interfaces use the ATA protocol. And the differentiation between interfaces and protocols and standards and stuff like that, I think it's difficult to understand the difference, but you can think of storage interfaces as something comparable to layer 1 and 2 of the OSI model. So you have a bit transmission and a communication protocol combined in the storage interfaces. And yeah, one of the most important ones is IDA, or Integrated Drive Electronics, also called PATA, Parallel Advanced Technology Attachment. So IDA and PATA are the same thing. It was renamed some time after IDE was invented. It was introduced in the 1980s. It's a parallel transfer method, and it was, as it's pretty old, it was used for older PCs and ATA-based HDDs. Then we have SCSI, Small Computer System Interface, also pretty old, also parallel, also for older workstations and servers. We have SATA, which you probably all know, Serial Advanced Technology Attachment, introduced in the 2000s. It is a serial transfer method. So PATA and SATA are basically like siblings, if you want to put it that way. The one is parallel, the other one is serial. It is still used for modern SSDs and HDDs. We have SAS, serial attachment SCSI, so based on SCSI. Also serial transfer method for enterprise storage and servers. Of course, we have USB. USB actually doesn't fit that well into that table, but for simplicity, I put it there. So it's the Universal Serial Bus, introduced in the 1990s. It has a serial transfer method for external storage devices, and it's actually very fast nowadays. And we have NVMe, non-volatile memory express. It works, it has a serial transfer method. It usually works over PCI Express, and it's used for high-end SSDs, modern laptops, and desktop PCs. And for all these storage interfaces, we have various connectors and form factors possible. Modern connectors can also handle several protocols. So just from the visual inspection of a connector, you cannot tell which protocol is used. So the connector is independent, and the storage interface is also independent of the storage technology. You can, for example, use STA for SSDs and HDDs. Yeah. And these numbers are all just approximate numbers from Wikipedia. You have so many dependencies here, so they don't take that or that one for like too serious. Yeah, so here you can see an example picture of an IDE connector. Yeah, you can see an HDD here connected via IDE to something. Here you can see an SATA connector, so you have a data cable and a power supply. Sorry, you have a power supply and a data connection. Here you can see an SSD with SATA interface and a SATA connector. As I said, it's still very common, but nowadays you also often see this NVMe stuff. Yeah. And why is that important? Because if you think about a digital forensics perspective, you may be required to come to a crime scene. You find several digital or electronic devices there. Maybe you have to open up one of these devices and extract the storage device. And then you have to know how it looks actually, what to expect from it, how to remove it. Yeah, maybe you have to build something in your lab, then you have to know about protocols, connectors, form factors, technology. Yeah, so this should just give you an overview over the most important things that exist out there, how they look, what they are capable of. Okay, there is a question in the chat. Can information be read out after deletion if we try to physically inspect the chips? Actually, yes and no. So as you already noticed, the controller takes care of the erasure, garbage collection and stuff. And if the controller didn't do it yet, there is a chance that you could get deleted data from a chip. So you would have to desolder it, read it out with an adapter. But the thing is, as the SSD distributes the data over the whole SSD or over the chips, over the cells, you will not find, or the probability that you can find data in a sequential order on a chip is very low,
ज़्यादा था ना तेरे पास
इसकी पड़ी
as it doesn't work
एक बड़ी
internally
वीडियो
like in
मैं
HDD.
वीडियो देखता
So
था
you could do it, you could try it,
इस साइड
but you probably
मेरी पता नहीं बहुत
just
सारी
get
कितनी
some
सारी
data.
एक दो तीन चार
Yeah,
पाँच
I know
पाँच
it's not a good answer, but it's physically possible, but
तुम्हारा ये नहीं
logically you wouldn't find your data.
तेरी
Okay.
दो है मेरी भाई
Okay, we have several interesting interface commands.
अरे यार पाँच
मेरे
साल
भाई की भी दो लेकिन
Yeah, so the computer interacts with the controller or the interface via drivers. This is why we actually have them. The controller sends a command to the hard disk via the cable to access the storage. Um,
जिस हिसाब से जा रहा हूँ मैं 2 साल में आते आते मेरी
yeah,
हर काम
yeah, I think we don't have to go very deeply into that slide. Yeah, you just have to know that drivers handle the communication with
मेरे को तो नहीं हो
the
रहा
storage device, and
कुछ नहीं हो रहा मैं ही नहीं हो रहा
yeah, they communicate over, for example, ATA commands over the storage interfaces.
एक स्काई डाइविंग के यार फिर कैंसिल हो गया
Okay. Questions regarding interfaces?
अब ये इतना सही लग रहा है मुझे तेरे पूरे मुंह पे एक दाना भी नहीं
Okay. So let's continue with flash chips. There are several kinds of flash chips. The most important ones are NOR flash chips, NAND flash chips, and embedded flash chips, for example, eMMCs. We already saw NAND flash chips when we had a look at the internals of an SSD. It is also the most commonly used flash memory type today. Because, as I said, SSDs use it, but you can also find NAND flash chips in USB sticks, sometimes in SD cards, but in SD cards nowadays you probably find eMMCs more often. NOR flash chips are more expensive, but also faster for direct readout. And this is why they are often used in an industrial context for storing firmware, for example. They are too expensive for consumer devices, but because they are much faster, they are often used in industrial settings. Okay. Okay, we can discuss copying stuff in SSDs afterwards, yes.
आजकल तुम्हें पता है हमारे इस आर्मी और
Okay, so here you can see an example of a raw NAND flash chip inside an SSD card, an SD card, not an SSD, SD card, a bigger one, where there's still like enough space to put it in there. The smaller ones, they are too small to actually contain a raw NAND flash chip. You have a controller here. So this corresponds to this picture here. So you have a NAND flash chip inside a package, and you have an outside controller, not integrated controller, which does all the host processes. For example, bad block management, wear leveling, stuff like that. And here you can see an eMMC chip. You can see these small ball grid, the small ball grid. It's actually, how do you say it? Something very special about eMMC. So you can, if you are not sure if you have an eMMC chip or a NAND flash chip in front of you, you could, of course, use the form factor, but also the general look of the chip to differentiate between those two. The raw NAND flash usually has these little feet here, which are used to solder it on the PCB, and eMMCs are usually soldered on the board via the ball grid layout. And that picture corresponds to that one here. So with eMMC, you have a NAND flash chip and an integrated controller. Inside that package, you have an NAND flash chip and a controller. And that outside package stands for like the device where the chip is part of. And since you have the controller integrated in your package, the host processor doesn't need to do that much because most of it is done internally. Okay, let me check my notes. Yeah, both technologies enable persistent data storage. They don't pretend to be a hard disk, actually, like the SSD does. Yeah, and this internal controller of the eMMC chip can be addressed via 64 different commands. They are usually 48 bits in length, including a memory address. There are commands for reading, writing, erasing, and they are specified by standards. For example, the JEDEC standard, it must not necessarily be the JEDEC standard, but the JEDEC standard is one of the most important ones. So the standard specifies the commands that can be issued to this integrated controller to get the data on the NAND flash. Okay, now let's have a very brief look on NAND flash cells. We talked about cells today a couple of times. What is it actually? So NAND flash chips consist of several NAND flash cells, and here you can see like a very simplified illustration of a NAND flash cell. And NAND flash cells are persistent transistors, and they usually have a substrate with a source, which is N-doped, a P-doped substrate, and a drain. And doping means that you introduce foreign atoms into a semiconductor crystal to specifically change the conductivity. You don't have to fully understand the process, just that you heard about it. And yeah, so transistors based. So NAND flash cells are persistent transistors, and transistors are based on the floating gate technology. And that means that the transistor is able to push electrons onto an electronically isolated gate. So we have the substrate here, we have a tunnel oxide. The electrons tunnel through that oxide, through the floating gate. We will see that in a second. And they can travel through this isolated gate, and then the electrons are captured and remain there, and they remain there even if the applied voltage is removed. So this is how data is stored in a NAND flash cell. Yeah, and as I already said, the NAND flash cell has a source, a drain, and a control gate where different voltages can be applied to generate certain states that represent bits. So to represent bits, electrons are captured or not in the NAND flash cell. And to read out written bits, again, different voltages, readout voltages must be applied to the control gate to measure the current and to interpret the measurement as 0 or 1. So the writing process is illustrated by these two figures here. So the picture on the left-hand side shows the writing process. So you have a certain voltage on the source, the substrate. You have ground on the source and the substrate, and you have certain programming voltages on the drain and the control gate. And because you have ground here and the voltage is here, the electrons in the substrate travel through the tunnel oxide into the floating gate, and then they are trapped there. And if you want to write a 1, you apply ground on the control gate and the programming voltages on source, substrate, and drain. And then the electrons travel back through the tunnel oxide to the substrate and create this state which can be interpreted as a 1. Okay, let me check my notes. Okay, and yeah, the electrons traveling through the tunnel oxide to the floating gate, this process is called hot electron injection. And as I already teasered earlier in this lecture, this process damages the oxide, which is why the write cycles of flash memory are limited. And this is what we know as wear and tear or wear out, and it reduces the ability of the flash cell to store charges in the floating gate. This is why we cannot program and erase cells like forever. Yeah, and this wear out is usually quantified in program erase cycles.
अरे यार ये तो लगा दुनिया को कैसे अरे इसने भी सूखी लिखा
And the process of the electrons traveling back from the floating gate through the tunnel oxide to the substrate is called, or is known as Fowler-Nordheim tunneling, where the electrons migrate from the floating gate back to the substrate. Okay. Yeah, so we also want to interpret these states and read out zeros and ones. And to read zeros and ones, a read voltage must be applied to the control gate. We need a sensor on the drain to measure the voltage. We have ground on the source and the substrate. We have for reading out a zero, we have a state where electrons are trapped in the floating gate. So no current can
किसी
be
ने तो बोला होगा
measured
तेरे
at a
दिमाग में
current
कभी नहीं आएगा
sensor because we don't have any electrons here.
देखा
And this state
बोल
of
रहा हूँ ना
not
मेरे को इतना तो
measuring
पता ही है
any
तू कहाँ
current
तक तेरा
here
दिमाग
is
जाता है
interpreted as
तेरे
zero.
दिमाग में फिट
And if we have electrons in the substrate, so the current can
बोल तू
flow
पहन ले तेरे को
from
भी जरूरत है
ground to the sensor,
इसको बोल तू पहन ले
we
तुझे भी तो जरूरत
interpret
है
that state as a 1.
अरे तो कुछ बोल रही है
Okay, questions so far?
दिमाग
Okay. Yeah, and you also probably heard about SLC, MLC, TLC, QLC. Maybe some of you wondered what does it actually mean. So SLC means single layer,
Bis morgen
single level cell,
Bis
multi-level
bald.
cell, triple
Abdul, तेरी
level
मर्जी
cell,
मैं निकल गया
quad level cell. And it actually means that you can
अब मैं तुझे नीचे
create
खड़ा करूँ
more states from one flash cell. So a single level cell is what we just talked about. You have a 0 and a 1, which can be created and read out through certain voltages. And for multi-level cells and so on, you have more threshold voltages, which can be interpreted as more states.
How do you
Um,
emergency
yeah, and this way up to penta-level cells encoding 5 bits are currently possible. Yeah. But yeah, increasing the states that one cell can hold or can generate also has disadvantages because it's the states are not as reliable. So quad level cells or penta level cells, the states are not as reliable as for single level cells, for example. Okay. Does only writing 0 wear off the NAND? I think so. Since the wear out originates from the floating gate not be able to hold electrons anymore, I guess this hot electron injection causes the wear out. So you usually, the natural state of a NAND flash cell is to have the electrons in the substrate. This is the, let's say, neutral state of the cell. And to change that, you need a hot electron injection, and you have to make the electrons travel to the floating gate. And this is what causes the wear out, because this is the normal state, if you want to call it like that. Nothing happens here. But with this, with the hot electron injection, something happens there, and this causes other effects. Okay, so I have a question for you guys. Now that you know what NAND flash is and also what eMMCs are, so the integrated, the embedded controller NAND flash, I was wondering if you know where eMMC is used. So we know that NAND flash chips are in SSDs and, for example, bigger SD cards and in USB sticks. But do you know where eMMC is used? Do you have any idea? Phones. What else? Micro SD, yeah. What else?
क्या
The cheap version of the
Sorry,
Steam Deck, I
come back,
think.
वही मैं सोच रहा था
Yeah.
वापस कहाँ आ रही है
What else?
एक चाबी के
Or
चक्कर में
where
कैसे
else?
खोलोगे?
Maybe IoT devices like bulbs. Bulbs, I don't think they have. Do they have like persistent storage? I don't know. I don't think so. I don't know. Good question. Have to research that. What else? Probably IoT, probably a lot of IoT devices and small chip embedded devices in cars, etc. Yeah. Think about your daily life a little more. Does any of you have, for example, a tablet? Refrigerators. Interesting idea. Yeah, I mean, you probably want to know which time it is because you were wondering when we are done with this lecture, for example, then you have a look at your smartwatch. Or after the lecture, I mean, it's Friday, maybe your lecture day is already over and you want to watch Netflix, then you probably turn on your TV. Or you instead want to read a book. So you probably you maybe turn on your smart e-reader. All of these devices have eMMCs integrated in them, like your smartphone, your Kindle, your Raspberry Pi with which you make your experiments at home, your smart TV, your smartwatch, your micro SD card, your tablet, like you name it, like almost every consumer device has an eMMC in it. And from a forensics perspective, this is very convenient and good for us because, as I already told you, raw NAND to read out raw NAND flash is difficult because yeah, you need to know about how the controller organized the storage in order to read it out in a meaningful way. But with eMMC, you have the controller integrated. So you could, for example, solder out the eMMC chip of this Raspberry Pi, put it in an adapter, and get meaningful data from it. This is usually not possible with raw NAND flash. So it's from a forensics perspective, it's good that all these devices have eMMC NAND in it, so it's easier for us to read the data from it. But because all these devices have eMMC in it, there's also a huge eMMC recycling market. And you may remember that I told you about the lifespan of flash cells and wear out and stuff like that. And recycling in general is a good idea, but if eMMC chips are not marked as recycled and sold as new eMMC chips, there can be situations where you could find old data from another person on the chip, and B, it probably hasn't as much PE cycles left as a new one. So yeah, so there is this recycling problem, but still from a forensics perspective, it's good for us that all these devices have eMMC chips built in. Okay, so that's it for today. I hope it wasn't too messy. Yeah, and if you have questions, yeah, please put them in the chat and I will try to answer them. Oh, there's a big one. Okay. Regarding copying process, how correct am I? Did I understand it correctly? Okay, 1. Let's go back to the slide very quickly. Okay, so strategy 1. Copy the block to buffer and delete the original block and then change the specific page, then write back the block again to its original block. Correct. So while you write the block back, you update the page. Strategy 2. The second strategy is to copy the page to another page and invalidate the original page and change the block and buffer and write it to the new block. No. So the second strategy says that you actually do the same thing as with strategy 1, but you mark the block, the whole block X, as invalid and write the buffer with your updated page to another new block, block Y. So it's the same thing, but this time we mark that as invalid and copy our data to another block. Okay, strategy 3. Bind the LBA address in the same block which has the free page. Okay, that's a very short version of strategy 3, but it's basically correct. You have the block, you want to update page 3, you write your updated page 3 to another page, and then you bend the LBA address to page 5. Strategy 4, copy the block to another block, considering the original has a free page, and while in the buffer, write to new free page LBA address to the newly copied block. No, for version 4 or strategy 4, you don't copy the block. You take a page from your block and write your updated data to another page in another block, and then bend the LBA address again. I think you mixed up strategy 2 and 4 a bit. But is it now clear? For clarification, we can write to a page that is empty but not overwrite stuff in it directly. EA just writes zeros and ones to the same page again. Why is that? Yeah, in order to, according to these strategies, in order to update a page, you have to write it to another page, because your smallest unit that you can write is a whole page. You cannot take one specific bit or byte and change that. You can only change a whole page. That's your smallest write unit. So you have to copy it to another place in order to update a piece of the page. Got it? You cannot address single bits and bytes. That's not possible. You always have to write at least 2 to 16 kilobyte. Could I copy the page and write the same page again? Apparently not. I mean, as I said, it really depends on how the manufacturer specifies the algorithms actually. According to Carl Weber, who wrote a technical report on SSDs in 2016, so maybe it's different today, but back then he identified 4 strategies to write a page, and these are the 4 strategies. I cannot answer the question to why you cannot overwrite the same page. Maybe because of wear leveling and garbage collection mechanisms. But yeah, according to these strategies, you don't write to the same page again. I guess because of their wear leveling. Yeah, exactly. Daniel is right. You don't want to write the same page over and over again. Okay. More questions?